So now, when we have an electron pair geometry of 4, steric number of 4, we're actually going to get 3 specific geometries, okay? And hopefully you can see by now the way this is going to work, the bigger the number gets, the more specific geometries there are, and it's always one less than the total. So for example, if there's steric number of 4, there's going to be 3 specific molecular geometries. When there was a steric number of 3, there was 2 specific geometries. And as you might guess in the coming slides, when there's a steric number of 5, there's 4 molecular geometries. So let's go through these. So the first one I'm going to start with is tetrahedral. So really this gives us, like, I like to think of this as like maybe the album, and then all of these 3 specific molecular geometries are like songs that are a part of this album. So here we've got the tetrahedral album, and we're going to talk about the hit track on the tetrahedral album, the tetrahedral shape. Okay, and the tetrahedral shape is given by, as you can see, 4 atoms bonded on the central atom. When we look at this methane and we draw the Lewis structure, we kind of draw it in this way that looks like a plane, right? Like this, which is what we did with trigonal planar. However, Vesper theory says, this is only going to have a 90-degree angle between bond to bond. These electrons want to spread out as much as possible because they repel themselves. So what happens, instead of making this planar geometry, it makes what we call a tetrahedron, okay? And a tetrahedron has slightly more than 90 degrees. So if I make this 90 degrees, right? The tetrahedron is technically 109.5 degrees, like that, right? Something like that, okay? So there's a 109.5. But now when I rotate this, I've got to make another set, another 109.5, okay? And it kind of almost looks like a pyramid a little bit, right? Where it can rest on my hand, perhaps, if I've built it well, if my hand is big enough to support it. You know what I mean? Okay, great. And now if I put, let's say, hydrogens all around, I've now got a beautiful little molecule of methane, okay, 3-dimensional. The Play-Doh doesn't hold up very well, okay? So this makes my lovely tetrahedral geometry. So these things should be sitting up. If you've got like styrofoam and toothpicks, that works really well also, okay? And so you can also see, for example, carbon tetrachloride. That's going to make a tetrahedral geometry. And the way we draw that, so when we draw this Lewis structure with all 4 things, it looks like it's 90 degrees, right? So the way we draw these things for a flat piece of paper is by drawing 2 lines right there. And those 2 lines, what they're really supposed to represent are the atoms that are in the plane of, let's say, the piece of paper. That would be this atom and this one, okay? So this atom and this atom are in the same plane, right? But now, let's see, the atom that's in the background, which would be this one, and the atom that's in the foreground, which would be this one, we represent with a dashed line and a wedge. So typically the wedge means it's going out at you, and the dashed line means it's going, in through the paper, okay? So that's how we can draw that to give us a 3-dimensional shape. And actually, let's see here if I can get this. There we go. That's how I know I've got it as a tetrahedron, right? And I can rotate it around, and oops, you can see my Play-Doh is failing here. And I can rotate it around, and it's supposed to be symmetrical, but I'm doing the best I can here. Okay, so let's see. Moving on. So still within the tetrahedral family, okay? Oops, now, so this one is supposed to be Trigonal Pyramidal, okay? or a trigonal pyramidal. And so now if I can do that by the following. So if I still stick with my tetrahedron, right? And I just remove one of these atoms and replace that with a lone pair, it still has four things around it, right? If you look at this ammonia, it's got three atoms surrounding the nitrogen and one electron lone pair. That's still going to make this tetrahedral geometry, okay? However, the angle is no longer 109.5. The angle is now just slightly less. And the reason why that angle is slightly less is because this electron pair, it doesn't have a nucleus up here to balance the charge of the electrons that are in this bond. So what it does is this electron pair repels this bond and this bond and this bond. So it kind of makes it so it stands up a little bit more, right? And so now the bonds between atoms, like the bond between this atom and this atom, is now 107 degrees instead of 109.5. I'm not so concerned with you memorizing these numbers as long as you recognize that the tetrahedral is what I'm going to start calling it, tetrahedral is 109.5. Now when I go to tetrahedral trigonal pyramidal, this electron pair repels those atoms down and it makes the bond between them shorter, the angle, and it makes the angle between the electron pair and the atom larger, right? Because it's repelling it away, okay? And so now, so that was our second geometry of the tetrahedral family. And then the final one is the bent geometry, okay? And so a great example of this is the water molecule. And so now if I remove one of these, and let's see, I need to start with a fresh atom here. So actually, yes, let's go to the red for oxygen. I forgot to use blue for nitrogen on that last example. Okay. So now, when you draw the Lewis structure of water, like is given right here, okay, it appears to be linear at first, right? It's just two atoms. And when you draw that Lewis structure, you draw it evenly, and we've kind of said, yeah, don't worry about it. It's, fine. Lewis structure doesn't have to represent the geometry. So then why is the water molecule bent like this? Well, it's bent because you can see it's got those two lone pairs. So that still gives it this tetrahedral arrangement of atoms, or arrangement of electron pairs around its central atom, right? But now when I put the two hydrogens there, okay, it gives it that bent looking shape, okay, which is pretty cool. So this is the way, you are used to seeing the water molecule drawn like that in that bent shape. What's not included here in this picture is you don't see those electron pairs. And just like what happened in the ammonia example, now because there's two electron pairs, it's pushing these bonds even more. So now the angle between hydrogens and water becomes 104.5. Okay? I think I have a summary of that. Yes, I have a nice summary of that right here. Okay? So the tetrahedral geometry, which is, I would say, by far the most common geometry we'll see in chemistry, can be given by the following. Look, 4, 0, 3, 1, and 2, 2. So 4 atoms with 0 lone pairs, 3 atoms with 1 lone pair, and 2 atoms with 2 lone pairs. That's how we get those pairwise options, okay? Because otherwise, if it was just 1 atom and 3 lone pairs, right? That just looks like this. And we just call that linear, right? That's just like an oxygen-hydrogen linear molecule, okay? Even though technically the electron pairs would still have a tetrahedral arrangement, right? Those 3 lone pairs around the oxygen, okay? So as you can see now, the bond angle decreases as we have less atoms, okay? So just recognize that the trend of these bond angles goes as is given in this picture. All right. Okay, so I'm going to go through these other